started आहे. ते हाईड कर आणि रे स्टॉप प्रेझेंटिंग.
दिसतंय का नीट सगळं? आपले तोंड दिसले पाहिजे ना?
अरे हो रे.
सो स्टार्ट करतो. माईक तोपर्यंत ऑफ ठेवून घे तुझं. So, good afternoon, sir. My name is Ayush Chaudhary, and he is my teammate, Rohan Chudekar. Today, we are going to present our SC on the topic of FE analysis on different types of pins. So, this is our content table. So, let's start with introduction of our topic. So, introduction of pin. And pins play a crucial role in heat transfer, serving an ingenious device designed to or efficiency of heat exchange processes, various heat exchange processes. Dated back in 19th century, this concept of extended surfaces or pins to improve heat dissipation was involved into various field of studies and applications. Fins are employed in various engineering systems, from heat exchangers and radiator to electronic devices, where optimizing heat transfer is promoted for efficient operations. So the basic fundamental principle behind fins lies in their ability to augment the surface area available for heat exchange, thereby facilitating a more effective transfer of thermal energy to the surrounding medium over the pinch design is very helpful and beneficial for various types of applications. Exploring different geometries, material, and configurations to maximize their heat transfer capabilities. So basically, there are various types of pins. The first pin is longitudinal pins. Longitudinal pins are very thin, elongate projections that extend along the length of a tube or a duct. They are commonly used in heat exchangers to increase the surface area available for heat transfer. Second one is circular pin, a circular pin or annular pin, we can call it. They are the pin structure with a circular shape, typically attached to the center core or bore. They are basically used in various applications where heat dissipation is very crucial. So circular fin used in very complex design like IC engines and various rack applications. So third one is rectangular fin. They are very thin, elongated projection extended from the base material to increase the surface area for heat transfer. They are commonly used in heat exchanger, electronic devices, and internal combustion engine, IC engine, to enhance heat dissipation. So this slide shows you what actually fins are. The first one is constant area pin. So as we can see here, the area from start to end is constant. Means the length and size of the pin is constant throughout. Second one is variable area straight pin. The this pin is straight in nature, but area of the pin is varying from section to section. So third one is fin. As we can see here, fin have tip at the end of the pin. So fourth one is circular fin or annular fin. They are circular in nature, and it is used in very complex design. So the basic purpose and significance of fins are: first, the primary function of fin is to augment the surface area available to heat transfer, thereby promoting more rapid exchange of heat between object and the environment or surroundings. The second one is by increasing surface area. Fins are enabled to enable the object to transfer heat more effectively and efficiently, either by releasing heat to the surrounding or absorbing heat from the surrounding medium. Fins are particularly beneficial in situations where space is very limited. As you all know that IC engine is a very complex design. So to dissipate heat from that engine, we basically use fins. Fins are very compact and it use very less space to withstand. So uh, uh, it significantly enhance heat transfer without uh, requiring large space on the object. And fourth one is this make them an indispensable component in many engineering applications. So further, Rohan will continue.
Thank you, Ayush. So I will further continue with our topic. So basically, it is CFD analysis on the pipe having longitudinal fin. So we have designed the geometry on the SolidWorks, and we have taken it over here for the analysis of the fin. So the photo is describing the mesh situation, and this type of fin is designed to improve the output of the triangular mesh on fin. Plate velocity is kept at 0.01 meter per second, and gauge pressure is 0 atmosphere gauge pressure. And the photo is describing the longitudinal fin and triangular meshes over on the fin. So we can continue further. So basically, the boundary conditions of the longitudinal fin are kept as follows. Inlet velocity of the water, that is a refrigerant, is kept at 0.01 meter per second, and the outlet velocity of the water is 0.01 meter per second. So the ideal conditions will be met, so that we have kept that conditions. So inlet temperature of the water, that is represent at the inlet, that is the blue lines that are showing in the photo at the left side. That temperature was 350 degree Kelvin, and outlet temperature that are denoted by the red arrows at the right end of the photo. It is coming with the less temperature, that is the fins have done their work, and it is about 300 degree Kelvin, and the symmetry used over here is longitudinal. So next one. So basically, the results that are of longitudinal fin, that is the temperature output. So here we can see that the orange color, which is at the left, extreme left of the photo, it is describing that the temperature over there was extremely high at the inlet. That means the fin as is given the high temperature refrigerant to the inlet, and the fins are getting done their work, and passing the cooled refrigerant to the VCR system or the system which are they are used in it. And basically it is saying that the fins have the only work to convert the high temperature refrigerant into low temperature refrigerant, and by the means of the long fins and the triangular meshes over here. So basically, the orange color is describing the high temperature velocity in high temperature refrigerant, and the light blue and dark blue color is describing the um, coolest refrigerant passing out through the film. So yeah, this was the explanation, and we can move further. We have detailed analysis report. We will open that and see the values taken over there. Moved on. We will move to material. Material properties was density. upward. Yes. Material properties were density was 998.2 kg per meter cube. Specific heat was 4182 joule per kg Kelvin, and the thermal conductivity was zero point 0.6 watt per meter Kelvin, and the viscosity was 0.001003 kg per meter second. Molecular weight as the was 18.0152 kg per Kelvin meter mole. So air and further was also taken as the default. So we can move further to cell. So material name was water liquid. That is, we are considered as refrigerant for our purpose in REC RC. So we will move further. Solid, move upward, Ayush. Solid part longitudinal fin pipe. The material name was aluminium, which we have used as ANSYS part. So we will move further to boundary conditions. So here the inlet velocity specification method was magnitude and normal to boundary, and reference frame was absolute. Velocity magnitude was 0.01 and the temperature was 350 Kelvin, and the outlet temperature was 300 Kelvin. So move further. Gauge pressure, that is PA, is in zero and normal to the boundary, and the total pressure specification was uh, normal to the boundary. We can move further. Wall. So material name was aluminium, sorry, and the thermal BC type was coupled. So for the same fin surface, material name was aluminium and the thermal BC type was mixed. So convective heat transfer coefficient was pi and the free steam temperature was 300. Side walls was also aluminum and thermal BC was via system coupling. So wall part longitudinal fins pipes part solid was also aluminum, and we can move further to report. Report is downward. So basically, velocity was almost 0.00099851 meter per second, and volume pressure was 0.001694 pascals. Part solid, that was the the one which was 0.0041 pascals. Volume temperature was 334.779 Kelvin. Part solid was 340, and the part longitudinal fin, that is 330. So these are the plots on the graph for better understanding, and we can close the PDF. The bit below was contours and vectors. So just put a glimpse over there and we'll close the PDF. So further, we have also studied the first part, that was our longitudinal fins, and the second part is steady state thermal calculations. So first we have considered the geometry of fins on a box, and we have 50 fins placed over there, and it is depicted in the left figure, and in the right figure we have getting the image of the yellow, and the temperature at is depicted by 300 degrees Celsius, and the convections was 22 degree Celsius, and the environmental temperature was 24 degrees Celsius. Base temperature was 300 degrees Celsius. Heat transfer coefficient was 22 watt per meter square Kelvin. So we can move further. So heat flux, which is described in this slide. So here heat transfer coefficient is kept for this use at is 2.2 into 10 raised to minus 5 watt per mm square. That are the blue lines which are describing the minimum heat flux available at the tip of the fin, and initially uh, so Ayush, please move backward. Ayush. So basically, the color is going from left to right. That is blue, becoming more light blue, and then moving further to green and yellow. It is describing that the heat flux that is minimum at the tip of the end, and it is moving greater towards the bottom of the fin, that is towards the bottom of the base, and gradually the heat flux is increasing. So we can move further. Results, temperature output of the fin. So fin dimensions used were length of 50 mm, diameter was 5 mm, total number of fin was 50, and box dimension was 500 by 350 mm. So here the, as I said, the blue is the minimum, and the blue is minimum temperature, and initially blue is basically the outlet of the box. So we are getting inlet from the right side, that is maximum, that is detected by the red color. So we will get our output of the system towards the fin, and the fin will gradually do the work of cooling the refrigerant and passing it to the system again for the efficient work of the machine and the system. So here red color is depicting the highest temperature, and the blue color is depicting the lowest temperature of the fin and the system. So this was the working and the results of the fin. So please continue. So the conclusion will be told by Ayush.
So here is the conclusion what we gain from this product, this SCE topic. So conclusion is fins serve as a valuable tool for enhancing heat transfer in wide range of applications. The versatility, effectiveness, and adaptability makes them an indensib- uh, indensib- indensible component in modern engineering design. Here are some specific conclusions from the study that we have been done through FEM analysis of different types of things. So what we learned from this essay or from this topic, that rectangular fins are more effective than circular fins. First one. The second was thin fins are also effective at dissipating heat, but they have a lower surface area than rectangular fins. So rectangular fins have upper hand on thin fins. So third one is the effectiveness of fin can be improved by increasing the fin length or thickness. In so it has a advantage and disadvantage also. Disadvantage was increasing the fin length or thickness will also increase the weight and the volume of the fin, which is a disadvantage in some other application also. So here are the references that we have done research for this topic. And furtherly, thank you for listening patient. Thank you.
Thank you, sir.